In the world of scientific exploration, remote research is a fascinating journey into the unknown. Unlike traditional research conducted in accessible areas, remote research plunges into the depths of uncharted territories, areas with extreme cold climates, outer space where there is no gravity or oxygen, or even deep into the oceans. These are locations far removed from human civilization, where the environment is raw and unaltered. But what exactly is remote research, and how does it differ from its more conventional counterparts? Remote research refers to scientific study conducted in environments that are typically inaccessible to human life. These are typically places far removed from conventional laboratories and beyond the comforts of urban infrastructure. Now you're probably wondering, what qualifies as remote research? Is it the depth of the ocean, the vastness of space, or the isolation of polar ice caps? Each of these locations are remote in the context of scientific research and exploration, which are defined not just by distance, but by their extreme conditions and the challenges they present. Isolation in remote areas presents unique challenges. Researchers must be versatile, often handling emergencies that, in more populated areas, would be easily manageable. Minor health issues or fires can escalate into life-threatening situations. Sourcing clean water and food becomes a complex operation. Therefore, comprehensive training and emergency supplies for all potential scenarios are not just beneficial, they're essential. Transportation to and from these remote sites is another hurdle. With underdeveloped and non-existent roads, reaching these locations can be difficult. Equipment and supplies often require airlifting or transportation by cargo ship, adding layers of complexity and risk. The effects of social isolation, especially for those researching alone or in small groups, are profound. Researchers in regions with little sunlight, such as deep-sea locations or polar areas during winter, can experience severe depression. This is sometimes referred to as polar madness, where up to 60% of researchers on polar expeditions suffer from mental health issues like depression, sleep disorders, and heightened irritability. The dynamics of working closely with a few individuals, often strangers, can intensify these challenges. Lastly, the living conditions in remote areas are often basic and challenging. The lack of amenities like running water and clean washrooms, coupled with the need to construct durable shelters in harsh climates, can be very daunting. Communication is another major issue, with minimal infrastructure and the likelihood of language barriers. Remote research, as we've seen, often involves venturing into some of the most extreme environments on the planet. However, thanks to technological advancements, what was once a daunting and sometimes nearly impossible task has become increasingly feasible. Today, cutting-edge technology not only makes these remote areas more accessible, but also allows researchers to conduct their studies more effectively and safely. Let's take a look at some of the equipments that make this possible. The exosuit, a Canadian-made dive suit designed by Phil Newton and Nutco Research, is a marvel of underwater technology. This suit is equipped with a staggering 50 hours of oxygen support and can reach depths of up to 305 meters. Not only does the suit provide users with depth, the suit is fitted with sonar for navigation and ranging, a camera, and lights for visibility in the dark ocean depths. Additionally, it features a full duplex intercom for seamless communication. The remotely operated vehicles, or ROVs, come in various sizes, with micro ROVs being particularly fascinating. They are used in confined spaces where a diver can't go, like sewers and pipelines. Remotely operated platform for ocean science, known as ROPOS, is another ROV capable of diving up to 5,000 meters. It's equipped for subsea positioning, navigation, imaging, and sampling. Communication with ROPOS is advanced, utilizing a satellite system for live video and two-way communication with labs ashore. In the desert, we find the Nomad rover, an unmanned vehicle developed by NASA for desert exploration and other worldly ventures. It's equipped for sampling and transferring with a multi-sensor for immediate sample scanning. The Tumbleweed rover, powered by wind, was inspired by the desert's own tumbleweed. This innovative rover is being considered for Mars exploration. In space, astronauts rely on the Extravehicular Mobility Unit, or EMU, when venturing outside their spacecraft. Now, speaking of spacecraft, the International Space Station, or ISS, launched in 1998, serves as a floating laboratory. Here, astronauts conduct experiments impossible on Earth due to microgravity conditions. The ISS also facilitates international communication among astronauts from various countries. Communication in space research has two types: radio frequency and free space optical, also known as laser communications. Frequency is defined as the number of cycles of a wave per second, measured in hertz, while radio frequency communicates using electromagnetic waves, which are waves that are created between an electric and magnetic field. Free space optical operates at a higher frequency, sending information modulated onto optical frequencies over a channel to a receiving system. Remote research revolutionizes scientific methods, enhancing community engagement and access to distant ecosystems for in-depth studies and conservation. However, this method must be careful not to miss the subtle complexities of these ecosystems. It's pivotal in climate science for monitoring climate patterns and crucial in astronomy for expanding access to space data and collaboration. Overall, while remote research offers remarkable opportunities for knowledge and collaboration, it demands a balanced approach, emphasizing ethics, data integrity, and inclusive engagement to fully realize its potential while avoiding possible risks.